Hello, everybody. So we're still talking about the concepts that we need to understand before calculating the enthalpies and the enthalpy and the internal energy. And we talked about the effect of temperature. Now we want to discuss another important parameter, which is the pressure. We all understand the effect of temperature because it's something that we can see and we know by observation, by very simple observation for water, for example, around us. But for the pressure, it might not be as known as the temperature. That's why I would like to start this discussion with a short video. This short video that we will see is about, and I hope this is clear here. But just to clarify this is a flask that is filled with water at room temperature. It's closed, so there is no air that will go in or out of this flask, and it's connected with this tube to a vacuum pump. And there is this connection here that measures the pressure, as we will see. So this is the pressure. It's 14.7 psi, which is 1 atmosphere, and we can see that the pressure is constant because we haven't done anything. Everything is under atmospheric pressure. And now the vacuum pump, which is this machine, it's turned on, and when it's turned on, we can see the pressure decreasing. So now the pressure is going low. It's now less than half atmosphere, so it's going to get lower and lower. And as the pressure decreases, we need to take a look at the water. So at some point, you would see here that water starts to boil. So this boiling that we see here is done under the normal temperature. Water now boils at 25 degrees Celsius or maybe 20 Celsius. And the reason for this phenomena to happen is not increasing the temperature, but decreasing the pressure. And this is what we want to start the discussion on how the pressure affects the phase. So it's clear that we can boil the water without heating, but by decreasing the temperature, the pressure. I'm sorry. So to understand this, let's understand how things happen in this case. So let's say this is a container that's filled with water. So what happens in reality, that there is a pressure that's applied from the atmosphere on the water, and at the same time water applies pressure on the surrounding. So both pressures are there. There is one pressure that is normal pressure, or whatever the pressure that is around the liquid, and there is the pressure that the liquid is exerting on the surrounding. This pressure is a function of temperature, or before this. So if this pressure that's outside is more than the pressure exerted by the liquid, then the liquid stays liquid. So there is no boiling that we will see. And this is what we see under the normal conditions. You can see water is liquid, so it's not boiling. So for the boiling to happen, we can either increase the temperature. Increasing the temperature here, it's not this case, but increasing the temperature would increase this pressure until it reaches a point where this pressure is equal to or more than the atmospheric pressure. Or by reducing which is this case, by reducing the outside pressure until it reaches that pressure exerted by the liquid. So the point of evaporation is that the pressure exerted by the liquid exceeds the applied pressure. So it will exceed it either by increasing the temperature. So as we increase the temperature, this pressure increases until it reaches a point where it will exceed the outside pressure, or to keep this constant by keeping the temperature constant and decreasing the outside pressure until it gets lower than this pressure. So the condition of evaporation is that the pressure exerted by the liquid exceeds or is equal to or exceeds the applied pressure. So this is the explanation of the phenomena that we saw here. So we need to understand this in a more scientific way. So this pressure that the liquid exerts is called the vapor pressure. The vapor pressure is a physical property. It's exactly like the density, like the viscosity, like the heat capacity. It's a property of the liquid. And this property depends on the liquid and is function of temperature. Density is a function of temperature, viscosity is function of temperature, heat capacity is function of temperature, and the vapor pressure is a function of temperature. So this is a property of the liquid. And it represents the pressure that the liquid exerts on the surrounding at a specific temperature. What we see here in this graph, this is a very nice graph actually. So in this graph we can see the vapor pressure on y-axis in torrs or in millimeter mercury, and the temperature on x-axis. The common behavior that we would see for different liquids, we have diethyl ether, we have ethyl alcohol, water, and the ethylene glycol, that as the temperature increases, the vapor pressure increases for all of them. They increase with lower or different rates, they increase in different ways, but they all increase as the temperature increases. We would see here, for example, for the y-axis, we would see the scale is 200, 400, 600, 800, and so on, but here we have the 760 millimeter mercury or torrs. This is equivalent to 1 atmosphere. We know the 1 atmosphere is 760 torrs or 760 millimeter mercury. If we look at the curve of the water, you would see that water has vapor pressure that's very low at low temperatures, and it keeps increasing and so increases until it reaches a point where it intersects with the 760 millimeter mercury at 100 degrees Celsius. And this is a very important thing, and this is why we will, or how we will relate to the phenomena that we see. So at 100 degrees Celsius, the vapor pressure of water, which is the pressure that the water exerts on the surrounding, is equal to 1 atmosphere. And this explains why we can see the water evaporation starting at 100 degrees Celsius. Because at this temperature, the vapor pressure of water equals the external pressure, which is 1 atmosphere, and now boiling starts. For ethyl alcohol, it's called 78. It's at 78.3. For diethyl ether, 34.6. For ethylene glycol, is going to be way more than the scale that, or bigger than the scale that we have. So we cannot see this here. But it will keep increasing until it reaches the boiling point, maybe 200, 250. I don't know exactly the value. So based on this, we can see that we have more than one boiling temperature for the liquids. We can have boiling temperature at 1 atmosphere. If, let's say, if the applied pressure is 400 torrs, then water will boil at 85 or 80 something. Diethyl ether or ethyl alcohol will evaporate at 65. Diethyl ether will evaporate at 15 or 16 degrees Celsius. So we have different boiling temperatures depending on the applied pressure. And this is what we saw in the video before, and this is what we can see here. So that's why we call the boiling temperature under 1 atmosphere the normal boiling point. So when we say normal boiling point, we mean the boiling temperature under normal pressure, which is 1 atmosphere. So this is the idea of or the scientific explanation or the phenomena that we saw. And this vapor pressure has been studied a lot, and we have a lot of equations that describe the vapor pressure. One of them is called, well, the very famous equation is called Antoine equation. Antoine equation says that log the vapor pressure equals to A minus B over C plus T, where A, B, and C are constants, and they are function of the material, so or the liquid that we're discussing. So for each liquid, we have values of A, B, and C. We just substitute with the value of temperature, and we can calculate the vapor pressure. So the vapor pressure is a very, very important parameter that we need to understand well. There are many applications of this. One of them is something that we see at home, which is the pressure cooker. The pressure cooker is one of the things that we have in kitchen, and it's used to cook food that is hard to cook. So it increases the rate of cooking food. And there is scientific basis for this pressure cooker. So if you look inside this pressure cooker, you'd see that you fill it with water and with whatever thing that you want to cook, meat or whatever. And it's perfectly sealed. You see the design is that it's you close the lid and then you turn this handle so that it's perfectly sealed. So there is no air going in and no air going out. And when we heat the pressure cooker, the water will get the temperature of water increases until it reaches a point of evaporation. So the water that evaporates is going to be confined here. So as time goes, there is more water evaporating, more water evaporating. It's stuck here. There is no place for this water to go. So the pressure increases. The ideal gas law states that PV equals nRT, so the volume is constant, the temperature increases, and the number of moles increases. So the pressure will increase. And as the pressure increases, this water that is inside the pressure cooker is now under 1.5 atmosphere, under 2 atmospheres. So it will boil at temperature that's higher than 100 degrees Celsius. So this water that is inside this pressure cooker will evaporate at or will boil at, let's say, 120, 130 degrees Celsius, maybe more, according to the pressure inside. And now you can cook the food using water at temperature higher than 100 degrees Celsius. So this is why we have this design of the cooker. We have also here this small thing which is a valve, and this valve, the function of this valve, it's like a safety valve. It's to ensure that the water will the pressure will not exceed the design pressure. So because if it keeps building up pressure more and more, it at some point is going to explode. So you need to make sure that this valve is releasing the extra pressure, so the pressure inside is within the design limit. So for the pressure cooker, as we said, water evaporates and accumulates, so pressure increases. Water evaporates at higher temperature, so food is cooked quickly. So this is one example of this. So the vapor pressure is available in tables. This is one of the tables in the appendix. In the textbook, and in this appendix you would see here that the temperature is this is of course the vapor pressure of liquid water. So and it says here vapor pressure of water, and here it says the vapor pressure in millimeter mercury. The temperature is in Celsius. So you can see for any temperature, these are the temperature that we have, and for each temperature you have vapor pressures. These columns are the fractions, so this or the decimals. So this is 14.0, 14.1, 14.2, 14.3, and so on, or negative 14.2, and so on. So it's giving an example for water at 4.3 degrees Celsius. So this is 4.3, this is 4, and this is 0.3. So this is 4.3. It's 6.23 millimeter mercury. It's a very weird way of putting the numbers in the table, but this is how it works. So anyways, this is the table, because water is a very well-known material. It's well studied, so we have tables for the values of water. If we have something that's it's not water, then we need to use Antoine equation. So for Antoine equation, we have tables already that we have. This is the equation that we saw. This log the vapor pressure equals A minus B over C plus T, and this is in millimeter mercury, T in Celsius. So what we need to do is just to go to the table, look for the material that we are interested in, pick the values of A, B, and C, plug them in the equation, put the temperature, and then we can calculate the vapor pressure. Of course, in millimeter mercury. So this is the effect of pressure. This is a very, very important concept of the vapor pressure, so I hope it's clear. And we will continue next time to see the effect of both the temperature and pressure, and how we can see the effect of both of them together in the same place. So see you next time, inshallah. Goodbye.